challenged. Let's start with the basics. What exactly defines an ice giant? In our solar system, we have two main categories of the giant planets. Closer to home, Jupiter and Saturn are also known as gas giants, predominantly made of hydrogen and helium. So massive that their interiors are compressed into exotic metallic states. Further out, beyond the asteroid belt and past the orbit of Saturn, we find Uranus and Neptune. These are smaller than Jupiter and Saturn, but still far larger than Earth. Their traditional classification as ice giant stems from the idea that a significant portion of their mass, specifically their mantle, is composed of ices, different kinds of ices, but not the kind of ice you put in a drink. In a planetary science, ice refers to the volatile compounds like water, ammonia, methane that would be gaseous at Earth-like temperature but can exist as a solid or higher pressure fluid in the cold distant solar system. The prevailing model for Uranus and Neptune depicts a relatively small rocky core surrounded by a thick, super hot, dense fluid mantle for these, which is made of these ices, essentially a vast, slushy ocean of water, ammonia, and methane. Above this, a relatively thin atmosphere of hydrogen, helium, and small percentage of methane, which gives them their characteristic blue-green hue. And this ice-rich composition has long been the cornerstone of their classification. However, over the past decade or so, with advancements in telescopic observations, theoretical modeling, and insights from exoplanet discoveries, scientists have begun to find cracks in this seemingly solid ice giant classification. The cracks aren't dramatic, sudden breaks, but rather subtle inconsistency that have steadily grown more prominent. One of the biggest issue arises when we try the model their interior. The traditional ice-rich model struggles to perfectly match the observed gravitational fields, magnetic fields, and especially the incredibly low heat output of Uranus. Unlike Neptune, which radiates about 2.6 times more heat than it absorbs from the sun, Uranus barely radiates any excess heat at all. This suggests a very different internal structure and heat transparent mechanism, or sort of transportation for heat from A to B. Potentially less convective than previously thought, or with a different core composition acting as a insulating layer. Furthermore, when researchers run simulations of their formation, particularly looking at the conditions in the early solar nebula, it becomes challenging to accumulate enough of these ice compounds to form such massive planet in the current location. This has led scientists to re-evaluate the initial building block of these worlds. So if not ice giants, then what? This is where the debate gets truly fascinating, and where new classifications are starting to emerge. Two primarily contenders have gained traction, which is the rock giant and the methane giants. Let's look at the rock giants, which is a hypothesis, and let's look at this one first. The idea proposed that Uranus and the Neptune might have significantly higher proportion of rock and heavier elements than previously thought. Instead of a thick ice mantle, a substantial portion of their interior could be made of rocky material like silicate and metals similar to Earth's core, but on a much larger scale and extreme pressure, under extreme pressures. These heavier refractory material would have been abundant in the early solar nebula. A larger, perhaps molten rocky core could explain some of the gravitational and the magnetic field anomalies, and might even provide an explanation for Uranus's low heat flux by acting as more efficient insulator. Then there is a methane giant. So this is a next hypothesis. Let's discuss this. While methane is an ice in broader sense, the classification emphasize its overwhelming dominance. Some models suggest that the bulk of the planet volatile content isn't the mix of the water, ammonia, and methane, but rather methane is the overwhelming dominant ice. This is supported by the spectroscopic observation of their atmosphere, which shows a notable methane in abundance. This distinction might seem subtle, but it has the profound implication for their formation. If methane was the primary volatile, it implies different conditions in the region where they accreted their material to form the planet. What both of these alternative hypotheses share is a move away from the equal parts water, ammonia, methane definition of the ice in their bulk composition towards a more specialized and specific emphasis on heavier elements or a single dominant volatile compound. The classification debate isn't just about what they are made of now, but how they got that way, how they basically formed that way. Planetary formation is a complex dance of gravity, collision, and the gas accretion within the swirling protoplanetary disk around a young star. The traditional core accretion model for gas giants suggests that a solid core forms first from rocky and icy material, and once it reaches a critical mass, approximately about 10 Earth masses, it rapidly siphons in vast amount of hydrogen and helium gas from the surrounding nebula. This works well for Jupiter and Saturn. For Uranus and Neptune, the problem is are twofold basically. One is the slower accretion. In the outer, colder and less dense region of the solar nebula, where there are, where they are today located today, accretion would have been much slower. It's tough to form such a large core from a gas disk dissipates, which the gas dissipates, which typically happens within a few million years. Number two is the less gas. Even if they formed a core capturing enough hydrogen and helium to match their current masses within that time frame is a challenge, especially given the lower density of the gas so far from the sun. So far, it's quite far from the sun. This has led to the theories of the planetary migration. Perhaps Uranus and Neptune formed much closer to the sun, where more material was available, then migrated outwards to the current positions, scattering small bodies along the way. Or perhaps they formed much earlier in the part of nebula which is enriched with these specific elements. If there are indeed rock giants, it implies a formation environment rich in those heavier elements. If methane giants, it applies a region where methane was disproportionately available or efficiently trapped. Each proposed reclassification forces us to re-evaluate the chaotic dynamic processes of their birth. This isn't the first time our solar system's planetary classification have been challenged. Many of you will remember the intense debate surrounding Pluto in the year 2006. For decades, Pluto was the ninth planet. Then, with the discovery of Eris and other large Kuiper belt objects, it became clear that Pluto wasn't unique. It was the largest of a new class of object, also known as dwarf planets today. The reclassification was controversial, emotional, but ultimately it brought greater clarity and a more precise understanding of the different types of bodies in our solar system. Could Uranus and Neptune be facing a similar but less dramatic re-evaluation? The ice giant category, which while useful, might be too broad or simply inaccurate given the increasing amount of data that we get today. By refining their classification, scientists aim for a greater precision. It allows us to better predict their properties, understand their formation, and compare them with more accurately with the thousands of exoplanets that we have discovered till now, and discovering new exoplanets every year. Imagine if we found an exoplanet that was clearly rocky, massive, and hydrogen rich. but we are still calling it Uranus and Neptune ice giants. It would create a confusion and hinder our ability to build a universal framework for understanding planet across the cosmos. How do we settle this debate? The answer, as it often is in the space exploration, lies in going there. While we haven't sent probes to Jupiter and Saturn like Pioneer, Voyager, Galileo, Cassini, all of these were focused on Jupiter and Saturn, and even a brief flyby of Uranus and Neptune made by Voyager 2. We never sent a dedicated orbiter or probe to truly study these distant worlds in detail. This is precisely when the Uranus orbiter and the probe mission or a similar mission to Neptune is considered the highest priority for a large class planetary science mission in the coming decades. A dedicated mission would also allow us to directly measure the gravitational and magnetic fields. This would provide much more precise data on their internal mass distinction, helping us discern between ice rich, rock rich, or methane dominant models. Analyze atmospheric composition. An atmospheric probe could dive deeper, giving us direct measurement of the elemental abundance and isotope ratios, telling us about the building blocks of these planets. We also would need to study the heat flux, which requires detailed measurement of their heat output, and it would be crucial for understanding their internal convection and thermal evaluation. Moving on, we will also need to observe moons and rings. There existive moon system like Triton or at Neptune or Miranda at Uranus, and faint rings around these planets could hold clues about the early solar system and the planets' interaction with their environment. There are missing pieces of the puzzle that only direct, prolonged exploration can provide. Without these missions, we are largely relying on educated guesses and distant observation. The implications of this particular debate extend far and beyond our own cosmic backyard. As we discover thousands of exoplanets, we are finding that the planets roughly the size of Uranus and Neptune, often called sub-Neptunians or sub-Earth or super-Earth with thick atmospheres, are incredibly common. In fact, they might be the most abundant type of planets in the galaxy. And if we don't fully understand the composition, formation, and evaluation of Uranus and Neptune, our own ice giant, then how can we hope to accurately characterize and classify these distant worlds, namely the exoplanets? Are many of these exoplanets mini Neptunians or more akin to rock giants or methane giants in the composition is a big question mark. Understanding our own outer planet is like a Rosetta Stone for unlocking the secrets of the planet formation across the entire universe. It helps us build better models, interpret observation from distant stars, and ultimately get closer to answering the grand question: how do the planets form and what makes them so suitable for life? The classification of Uranus and Neptune as ice giants might seem like a small detail in the grand scheme of things, but as we have seen today, it represents a profound ongoing shift in our scientific understanding. It highlights the dynamic nature of science itself. By constantly questioning, observing, and refining our model based on new evidence. Whether they are ultimately reclassified as rock giants, methane giants, or some entirely new category, one thing is clear: Uranus and Neptune remains magnificent, mysterious world. They hold vital clues not just about their own story, but about the story of the entire solar system, and indeed the billions of planetary systems beyond the solar system itself. So next time when you look up at the night sky, remember these distant enigmatic worlds, and the quite revolution underway is how we perceive them. Their classification might be conflicted now, but with future exploration, the answers are waiting. Friends, thank you for joining me on this journey. Thank you for joining live. If you found this discussion thought provoking, please hit that like button, subscribe for more space content, and let me know in the comments below what do you think about Uranus and Neptune they should be called. So I look forward to receiving your comment. See you next time. Until that time, keep looking up.